Welcome to class. In this video, we're going to continue talking about power series solutions around ordinary points, so if you haven't seen the previous video, go check that out now. Let's take a look at an example where my coefficients are a little less nice. Here, I've got y double prime plus sine of xy equals 0. Now the good news is that's already in standard form, and we know sine of x is continuously differentiable, so we don't actually have any singular points for this differential equation, which means we could take a power series solution centered anywhere. So I picked 0 again out of convenience. I followed the same strategy. Here's y written as a power series, here's its second derivative. I plug it back into the equation. And you'll notice our first simplification step is already sunk because sine of x is not a polynomial that is going to play nicely with cleaning up these power series. At least not in the way it's written right now. Well, perhaps you recall that we can write just about any continuously differentiable function as a power series, and we call that a Taylor series expansion. For sine of x, I'm going to center it around the same point as my power series, so around 0. And I write this as, perhaps you recall this has more of this is a good one to remember, a good Taylor series formula. It's an alternating series where I have x to the odd powers over that power factorial. So here I just went ahead and swapped sine of x for that power series in my representation. Next thing that I want to do. Power series do not multiply as nicely as they add together, even if they're in phase. Remember, these are really just really long polynomials, and when I multiply two polynomials, I have to distribute. I don't factor, and I don't want to get into double summing anything here. So instead, let's brute force it, and let's look at the first, say, 4 terms in each power series. I'll come back with those written up. And there we are. Here's the first few terms of this power series for y double prime. And here's the first few terms of my power series for sine, and the first few terms of my power series for y. And what I need to do next is distribute. So what you'll notice is, when I distribute the x, I will bump my power series up by 1. When I distribute this guy, I will bump it up by 3. When I distribute this guy, I'll bump it up by 5, and so on. So I'm going to clean the board and write out the first couple terms of what each of those look like. All right, so remember what I'm doing is I'm starting from my power series for y double prime, and then I'm adding on the power series for sine times the power series for y. The first term in that product is going to be x times the power series for y. So here's the power series for I with its degree shifted up 1. The next term is going to be x cubed over 3 factorial times the power series for y. Here's that guy, and so on. But what I'm doing at the end of the day is adding all of these up. And so if I match columns, I've written this strategically so that we can see the coefficients on every degree of x. If I factor out like terms, I get that in terms of constants, I just have 2c2. In terms of degree 1, I have 6c3 plus c naught x. In terms of x squared, I have 12c4 plus c1 x squared. In terms of x cubed, I have 20c5 plus c2 plus c naught over 3 factorial x cubed, and so on. And this is a power series. It's just that I don't have an explicit or recursive formula to figure out my coefficients. Instead, I've just brute forced it. And we learn a couple of things immediately. From that same strategy as before, we know this should be 0. So each degree, or each set of parentheses I have here essentially should equal 0. So from the first one, I learn that 2c2 is 0, so that immediately tells me c2 is 0. Cool. From the x terms, I learn that c3 is c naught over 6. Great. Going to continue the pattern here. I learned that C4 is C1 over 12. Now I'm going to be able to start reusing information because I already know C2 is 0, right? So I know that C5 is whatever C0 happens to be over 3 factorial. Oh, well, hey, that's C0 over 6. That is just C3. So I get C3 over 20, and so on. And if you continued this pattern out a little further, you would notice that I cannot resolve or determine all of my coefficients because I have no direct way of getting C0 or C1. In other words, C0 and C1, we would describe them as free variables or free parameters. Remember that there are many, many, many solutions to these linear homogeneous differential equations. And at the end of the day, since this is second order, we really only need 2 fundamental solutions, or 2 linearly independent ones. So we can just choose arbitrarily C0 and C1. Any power series of this form is going to be a solution, so let's just pick a couple of them in particular that are going to be linearly independent. How do I do that? Well, there's one really easy mistake to make that is bad, which is I like 0. 0 makes things easy. Let's pick 0 for both of them. But do you notice if you pick 0 for C0 and for C1, then every coefficient is 0? While you're technically correct that that's a solution, it's the trivial one, and that's not very interesting, right? We are looking for 2 non-trivial linearly independent solutions. But here's the strategy. Notice for my second order equation, I have 2 free parameters. Let one parameter survive per fundamental solution. In other words, if I take C0 to survive and C1 doesn't, let's see what happens. Well, I know C2 is equal to 0. There is no constant term. Okay. C0 is 1, which tells me C3, right? This tells me that C3, well, we know C2 is always 0, right? C3 is 1/6. C4 is 0. C5 is C3 over 6. That's 1/6 times 1/20th, or 1 over 120, and so on. If I pick the other way, if I let C0 die, and C1 gets to live, gosh, that sounds really morbid when I say it that way. I'm going to stop that. C2 is still 0. It's always 0. C3 is 0 now. C4 is going to be 1 over 12. C5 is 0, and so on. So I'm going to clean up the board, and I'm going to write these 2 different cases down. And here's what we arrived at. If I choose C1 to be 1 and C1 to be 0, here's the solution I get. But if I make the other choice that C1 is 1 and C0 is 0, here's what I get. But do you notice that there are no matching powers of x across either power series? Together, they give me every power of x except for x squared, but that's okay. We knew x squared's coefficient was going to be 0, regardless of our choice of free parameters. So what I just found were 2 linearly independent power series solutions. Maybe I'll call this y0 since C0 was 1 and y1. And now I know that the general solution is a linear combination of these 2 by principle of superposition.